Okay, welcome class. This is going to be a repeat of the class we did last week on the ZeroState Response, chapter 12, okay? Because we lost a bit of time trying to get the AV to work and then it didn't work in the end anyway. All right, so let's begin. Let's remind ourselves what we mean by the ZeroState response. It's the time-dependent response of a system when the initial state is zero. Okay, it's the time-dependent response when the initial state is zero. Now, for a linearized, the initial state is zero can be a bit confusing, but for a linearized system around a steady state, this means that there are no perturbations delta x in the steady state variables. It's not that x is actually at zero, it's just that we haven't perturbed it, and it's basically delta x is zero. Okay. Now, the fact that delta x is zero implies that the zero state suggests that there's actually a change in the input, and that is indeed the case. So the zero state response is all about looking at changes in the inputs. Okay. So here are some of the topics we're going to do. We're going to look at the time-dependent zero-state response, its relationship to the convolution. I'll show you a simulation I did of the convolution that actually does the convolution. The relationship between the Laplace domain and the convolution. A couple of bits on terminology, the resolvent and the time transition matrix. Then transfer functions, poles and zeros, the order of a transfer function, poles and zeros plot, and then the final value theorem. Okay, so it's quite a few topics here, but that's what's in chapter 12. There's a couple of things one or two things I missed out, including block diagrams. I don't use them much in this class, but a following class may use them, and you get introduced to them then if you take that. Okay, let's have a little reminder then, shall we? So, okay, so I see the screen isn't big enough. Never mind. Okay, so let's look at this really simple system. Okay, so this would be something like, so we'd have X, we'd have a production of X. There's some input there, it could be a step input, impulse, whatever. And then we have some consumption of X at a rate Kx, okay? And this is the differential equation that describes the change in X. So Qt is the input signal. I'm going to try and use Q from now on rather than U, because U suggests step response, and that's not always what we're talking about. So Q is the input signal, currently undefined, okay? So to compute the zero state response, we set, of course, delta x 0 to 0, and we apply the Laplace transform to both sides to yield this. Okay, so remember, these things are the this is how we represent the transform of x itself. And since we don't know what q is at this point, we'll just represent it as q of s, okay, capital Q of s. Of course, we can solve for x, and this is the equation we get then. So x of s is q of s times 1 over 1 plus k. Notice how the q term appears to be separate from another term. And in fact, you'll see that all the time, okay? You'll always be able to maintain a separation between the input signal and this other piece here, okay? And we haven't got a name for that piece here, but I can give you a hint. It's going to be called the transfer function, okay? Now, if I were to, actually state what the input is, maybe we make the input an impulse, unit impulse, right, delta t, then of course q of s is 1, right? So remember that the transform of a unit impulse is 1, so basically the q of s just disappears. We end up with this, okay, right? So this is the unit impulse response for the system. Now I can have different strengths to the impulse. I could have a strength k to my impulse. In that case, all that happens, and this is the key point here, is that the x of s just gets scaled. And in fact, by the value of the strength of the impulse. In fact, this is reflected in the time-dependent solution as well. The time-dependent solution just gets bigger according to the size of the strength of the impulse. Okay, so that's why I put this here in bold, because it's quite an important point. And we'll use it when we come to talk about the convolution. So changing the strength of an impulse simply scales the transform, and in turn scales the time-dependent solution. And of course, this is all because the system is linear, right? That's why we can do this. Okay. So just a summary then. So the impulse response of a system, the impulse response is the output of the system when we apply an impulse, surprise, surprise, to the system with all initial conditions set to 0, okay? And then this is where we come to now interpreting this piece here, okay? The 1 over s plus k. The response of a system to an impulse in zero state is called the impulse response and is described by the transfer function. Now, I will always use h of s to describe the transfer function, okay? So x of s, so if you think of it back here, I can rewrite this as x of s equals k times h of s. So h of s is the transfer function, this piece here, okay? All right. Okay. Right. Okay, so now we come to the convolution. So why are we bringing in the convolution? Well, it turns out there's a really close relationship between the convolution and the zero state response, okay? You probably may or may not remember, but this is the convolution, this nasty looking thing, this integral. The question is, what does this mean? And this is what I want to talk about here. In particular, what does this term mean? What does this term mean? This, of course, is the output, okay? Or this is the response x. All right, so if I had that little system we had before, that's the x in that system. Okay. So first thing I'm going to do is, I mean, this just looks like an input, but it's a little bit more sophisticated than that. This looks like because I'm using Q, this looks like the input function. It is, in fact, that, but it's a little bit more sophisticated. In fact, I'm going to define it in terms of an infinite number of impulses that I apply to the system, and each impulse is going to be scaled by the strength of the input. All right, so this is equivalent, this piece here essentially is equivalent to this piece. So this is just a recasting, right, of an input function in terms of impulses. Now, if you go to the textbook, it gives a proof of this. It's pretty straightforward, but it's a way of expressing an input signal, any input signal, in terms of a series of impulses where each impulse has a given strength, okay? Now, so in the convolution integral, which is this thing here, we saw that Q is the input. Now H, this actually relates to the use of HS. So HS is the response of the system to a unit impulse, okay, unit impulse. So little h is actually the time-dependent response as a result of a unit impulse. So h of s is the response of the system to a unit impulse, okay? So all I'm doing here is I'm taking the unit impulse and I'm multiplying it by, so for a given time tau, for example, I'm taking the response at tau, all right, if I applied an impulse of strength Q. That's basically what's happening here, all right? And I do this for all time, right? I basically have thousands upon thousands of impulses. Each time I apply an impulse, I measure the response, right? Now, of course, I should do these impulses one at a time. I can't do them all at once because I have to wait for the system to settle back before I can try the next impulse. That's how I would do it operationally. But that's what this expression basically says. So just to say, so the convolution, okay, is interpreted as the sum of a series of impulses along the timeline with the strength determined by the input signal. These impulses are used to scale, oops, there should be a space there, scale the unit response of the system H. This is why I emphasize the idea that when we did it back here, I emphasized the fact that an impulse of strength K will just scale the response. It's just a scaling factor, that's all. And that's what we're seeing basically here. This is acting as a scaling factor for the unit response. But of course, now this is in the time domain, not the Laplace domain. So that's all this is. So let's make sure we understand what this is. So I've got a diagram here, figure. So what we've got here is the the response, the overall response. Okay, so I have some system, and the blue line is actually the response of the system as a result of some input signal. Okay, and I'm suggesting that this blue line is actually the convolution of the input and the unit responses. So these red lines here, right, these red arrows here represent the impulse. And you notice that the lines are at different heights. That's because the signal I'm inputting into the system looks something like that, okay? All right, so you follow the heights of the impulses. It shows it looks like something like this. Now in reality, of course, I'll have an infinite number of these, right? But I can approximate it by having impulses at distance delta tau. Okay, so that's what this means. So every impulse is applied at a distance delta tau from each other. And each time I do it, of course, the system responds. All right, and the system responds by, I mean, who knows how it'll respond, but in this case, it's responding this way. It goes up, and then because the impulse only happens for a moment, it then decays back. Okay, all right, decays back, and each time I do an impulse, the system will respond to that impulse. Okay, all right. So that's what this indicates here. These are all these curves. Each of these curves happens. There's n of them. So that's what the n is. There's n of them, and each one occurs at n delta tau. Right, and I have a whole series of these. Okay. Now, what the convolution does is basically sums all of these. It basically sums them, all the graphs. It basically forms a one big sum. So it takes for a given time point, right? For a given time point, it'll take this number, 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 and sum them. All right. But it also multiplies by the delta tau. Otherwise, you'd end up with infinity, of course. So it sums them and then multiplies by delta tau. So if I go back to here, this is the delta tau, basically, right? It sums them and then multiplies by the delta tau. All right. Now, when you do the integration, of course, you've taken this to the limit where delta tau is infinitesimal, and then the integration technique does its magic. But if you were to do it approximately, this d tau would turn into the delta tau. Right, so I have to remember when I do the summation is I have to this entire thing here, this product is the orange curve, right? Is the orange curve we see. Oops, sorry, is the orange curve we see here, right? And we need to remember to multiply by delta tau. So I would take each point, right, add it up and multiply by delta tau. And that will give me this point up here. Okay. All right. So I can actually do a simulation. I could actually, I mean, this could be done, right, in the simulation. I can apply, at least approximately anyway, I can apply a series of impulses and measure the orange lines and then add them all up and see if I actually get the response, right, x of t. So let's try it on this little simple system here, okay? So it's this little simple system we've seen before. We're going to apply a series of impulses to the input, okay? Apply a series of impulses to the input. Then I'm going to look at what happens to x, okay? And just to keep things simple, I'm going to apply a unit size impulse. So this is effectively a step input. So if I were to plot against time, the input, right? It's basically a series of impulses. And they're all going to be at value 1. These are all unit impulses. So effectively, I'm simulating a unit step. All right. And I've got a few of the responses here. Okay. So this is time. This is time down here on the x-axis. And this is the response in x. All right. So what happens is we get this impulse. It's sort of, you bang, the system gets an input for a moment. And then x, basically what you see is an exponential decay in the value of x. Okay. You think it would rise then fall, but it doesn't. It gets an instantaneous value and then falls. All right. Notice it's not at 1, but it's at roughly around 14. Okay. So the input gives it a real kick. and kicks it up to 14 in this case, and then it drops back down. All right. Because what I have to do then operationally is I have to let it settle down, and I have to start again, and then move my time to the next one and give it another impulse. Again, it reaches just under 14 because it's basically the same thing, and then just decays back again, right? And then I do it. I move on again. I do the next impulse. So I can do this, many times. And what I need to do then is I need to take for a particular time. I just need to take all these points here and basically add them up, and then multiply whatever my delta t was, and that'll give me the output response for x of t. All right. Okay, so this is the software. I wrote a quick Python script to do this. So this is our system here, right? It's the one we've been talking about, the simple one. My input is going to be x of t, okay? I know what the steady state is. All this is done relative to the steady state, right? So I'm going to compute the steady state here, and I'm going to set the value of x to the steady state, all right? So this is going to start at steady state. Then I'm going to apply an impulse. Now, this piece here is what does the impulse. So the impulse will happen at the time start, and at the beginning start is 0, okay? So at time start, I will add 1,000 to the input, all right? Then very shortly afterwards, at a delta t of 0.001, I bring x back to what it was, which was 10, right? So it's 10. It was 10 before. Now I'm ensuring here, because I want a unit impulse, I have to ensure the area of the pulse is 1, right? So 1,000 times 0.01 is 1. So I'm going to ensure that gives me the unit impulse, right? Remember, the value of an impulse is basically its area. Okay, so when we talk about the strength of an impulse, we're basically talking about the area. But in this case, I want a unit impulse, so the area has to be 1. So I have to make sure that the product of these two, right, the height times the width must be 1. All right. So this basically does a single impulse at a given time start. All right. Now the next thing I'm going to do, I need to produce a reference trajectory. This is basically the steady state. All right. And the way I'm going to do this, I'm going to set the start to 100. I'm only going to go up to 40. So these at statements never get fired. Okay. So that's why I pushed it up to 100 here. So this gives me the reference values for x. Okay. Basically the steady state, basically. All right. And what I'm going to do is I'm going to sum every time I do an impulse. I'm going to add it to the ref, right? So I can build up the response. Okay. So this is now the full thing. I've got the model up here. I've got my reference trajectory there, and this actually does the convolution. So I'm going to start at time 0. I'm going to run this. I'm going to do 25,000 impulses. Okay. So I'm going to run the simulation here. This will apply the impulse at whatever start is. In this case, it's 0. So it'll give me something like this. So what happens is if I in the first time round, I'll get something like I'll get an impulse, and then I'll get a decay. Okay, that's what I'll see at start 0. All right. At a later time, say start 10, I would see something like that. Okay. All right. Now I'm going to do 25,000 of these. So every time I do them, I add this curve basically to the reference point. I have to take away the steady state value, right? And then I add that to the reference point. Okay. I have to remember, however, I have to remember to multiply by the delta t, though. That's crucial, otherwise it won't work. And the delta t was 0.001, okay? It's 0.0001 because that was basically the width of the impulse, right? So I've done the first impulse. I'm going to plot it, just see what it looks like. And then I'm going to add delta t to the start, all right? Restore the steady state just in case, all right? And then I go back again and do the same thing. I do this 25,000 times, okay? That basically does the convolution. Now, I'd like to compare the convolution result with if I applied, where is it, the step input, right? Effectively, I'm doing a unit step input. So what I can do here is I can rerun the model, do the same model but different instance. And this time I'm going to simulate an actual step input. So time greater than 0, I'll bump x0 up by 1. That's effectively a unit step input, right? And that's the same as if I applied a whole series of unit impulses. So I'm just going to do this for comparison, okay? I want to compare how an actual step, the usual way we do a step input, right, which is this way, compared to actually doing the convolution. All right, so here's the result. So these are the 25,000 impulses. Now, it's pretty dense. So if you looked at any one of those, it would look like that, okay? So any one of them at a particular time t looks like that. It's basically an exponential decay. And I basically stop here. This is where the 25,000 impulses stops. What you're getting here are all the decays from all the ones just beforehand as a decay to 0, okay? Now, this is the true solution here, the second one. This is the true solution, which I got by doing, a step as we'd normally do. This, however, is the one that was computed, okay? And it only goes as far as 25, of course. There's 25,000. I only went as far as that. Now, looking at this, I thought, I don't know whether those two exactly the same or not. So what I did, I merged them. I put one on top of the other, and they are exactly the same, okay? So this line here is the true solution coming off, and this one here is the convolution. And you can see right up to the 25,000, it's exactly the same. So the convolution really has computed the step input. All right. This is basically how the convolution works. Just to show you, I don't have to do 25,000 impulses. I could do 25 impulses. This time I need to, I'll make the impulses wider, say 0.5 time units. I did this so you can see the actual you can see here the individual impulses and each individual decay. If I sum this up, I get this, right? I'm only going up as far as here as well, right? But you can now see the approximation is very jaggy, right? Basically, I'm summing up thousands and thousands of exponentials. In this case, only 25 exponentials. So you can see it gets a little bit rough, okay? So if you want to do this computationally, you need to be able to sample large numbers of impulses to get this to work. Okay. So in summary then for this convolution, so the convolution is equivalent to a ZeroState response, all right? But it's described in the time domain, right? Not the Laplace domain. And just to summarize then what we have here, this piece, the H is the unit impulse at tau. This is the input signal at tau scaled by an impulse. And then I'm summing over all the responses. And then I get the overall response. Okay. So that's all the convolution is doing. Okay. Now, of course, this integral, is non-trivial to compute. You need to get H to start off with. That's an integral in its own. And then you have to do this integral itself. In fact, there's an easier way of doing this. There's actually a nice relationship between the convolution and the Laplace domain. I'm not going to give any proof here, but notation-wise, because this is, complicated, this whole thing looks very complicated. Notation-wise, the convolution is often expressed in this way. So QT, and then it has a star H, all right? So it's often more simply represented using this notation. And the result, I'm not going to give you any proof, but the Laplace this is the Laplace transform operator. The Laplace transform of a convolution is simply the product of the transforms of the individual functions. Well, that's an amazingly clean result. Okay, so this complicated convolution here in the Laplace domain is just QS times H of S. No integral, it's just a multiplication, right? So in the Laplace domain, X of S, that's what this is. And of course, we've yeah, okay, we've actually seen this before, but I'll come back to that in a minute. All right, so and it goes in reverse as well. So if I take the inverse Laplace transform of a product of two transforms, I'll get the convolution. So this actually provides an easy way to compute the convolution. If you know your input, compute its transform. You know the other piece of the equation, right? The h of s. Multiply the two together, then take the inverse, you get the convolution. Much easier. Okay. So let's now, so I'm basically now moving from the time-dependent solutions to the solutions in the Laplace domain. So just as a review, this is the homogeneous equation, right? Right, in the time domain. If I take the Laplace transform of this on both sides, I get this, all right? So every time there's an x of t, I do x of s, and I got the a there. This is the homogeneous expression, so x of s is not equal to 0, okay, so it's here. I can rearrange this, and I can rearrange it, and I get basically this, okay? What's interesting here is this term here, okay? Because you've seen this before as well. You saw this when we were looking at the eigenvalues, right? And this will come back to us again. I mean, this whole thing sort of is very circular. It all wraps up and everything is connected with everything. But you see here now, that looks like the part of the eigenvalue problem, okay? And we're taking the inverse here, of course. In terms of notation, this thing here actually has an important name. It's called the resolvent, okay? It's called the resolvent. So this thing here is called the resolvent, right? You see that in a lot of books. Now, if I were to take this, right, if I took this, right, and I took the inverse transform of that, I would actually get the solution in the time domain, okay? So I take the inverse transform. Now I can multiply the inverse transform doesn't have to include x of 0 because x of 0 is a constant, okay? Because that's the initial conditions. And I get that out. How can we interpret this thing? This in the scalar world, this piece here is actually this, okay? In the scalar world, it looks like that. Now that is there's actually a series expansion for this term. It's not a common one you'll see in the series expansion tables, but you can easily work it out using a Taylor expansion. But you basically get this. And by analogy, and I'm not going to show the proof of this, by analogy, I can move this into the matrix domain and I get this. And some of you may recognize that as the matrix exponential. Oops, matrix exponential. Okay, and of course the exponential is this. So in fact, the inverse of this piece is actually the matrix exponential. All right. So here we see all the connections happening between the various bits that we've done. Okay, so this just summarizes it then. So the inverse transform of the resolvent, this piece here, is the matrix exponential. And therefore the solution, as we've seen before, is simply the matrix exponential times the initial conditions. And we've seen this before, okay? This just summarizes what we did. The inverse of the resolvent is the matrix exponential. Another piece of notation, this piece as well is also called the state transition matrix, okay? And is given the symbol phi, all right? So phi, okay. All right. So that was for the homogeneous case, right? Where was it? The homogeneous case, this piece here. Let's now look at the full response, including changes to x, the state variables, and changes to the inputs, okay? So this is going to be the full response, okay? The full response. Now, you probably don't remember, but the time domain solution for this full response was this nasty looking thing here. This piece here, of course, you see from here, right, or maybe this bit, right? That's that bit, okay? This bit, though, was something we haven't talked about, but I did hint as to what it was. I'm going to use Q here instead of U as I used before for the input, but other than that, it's the same, right? So this is the time domain solution. So let's look at the Laplace transform of the full state equation. So this is the full state equation, right? Remember, that's the linear time invariant system. I'm going to take the Laplace transform on both sides. I get this. Okay, this is the full system now, so I have to include x of 0 as well. Collecting terms, I just get this. So the input is turned into Q of S. Okay, just be aware of that. And I now just solve for x of S, and I get this. Okay, so this, of course, you've seen before. This is the resolvent times x of 0. But now I have this new piece, which is the non-homogeneous piece, where again you see a resolvent times b times whatever q is, right? I've not specified the nature of the input here. I just called it q of t, but in the Laplace transform domain, it turns into q of s. I can now take the inverse transform of this, and I get this piece. Of course, that's e to the at, and I get this piece here. Now, I have to take the inverse transform of the whole thing. Here, I could take the x of 0 out because it's a constant, but I have to include the q of s inside the inverse transform, okay? I can't take those out. So the question is, what is this? Okay, question is, what is this? All right. So let me see. Actually, that's just a repeat. Okay, let's just repeat of that one. All right. So what I'm going to do is I'm going to take this, all right, and I'm going to, let's see, what am I doing? I'm going to denote the resolvent by this, okay? So I'm just going to put that there, okay? And you'll notice now I've effectively got two transforms. I've got this piece here, which was the resolvent, and I've got this piece here. Right, there should be another bracket there. And I got this piece here, which refers to Q of S. This is a product of two transforms. Remember, the product of two transforms, or the inverse of the product of two transforms, is the convolution. Therefore, this actually is the convolution. Okay. I know what the inverse of this is. It's just EAT, all right? And then the inverse of this piece is just BQT. I can express this fully using the integral instead of the star notation, and I get this. Okay, this effectively is the convolution, right? So we see that the time-dependent solution for a full system includes this piece, which is the non-homogeneous piece, and the convolution. That basically tells us how the input causes the system to respond. All right. Now, somebody in class asked, we're going from 0 here instead of infinity, because the convolution before was defined to go from minus infinity. We can do that because I can assume that, there's nothing present. This is time, okay? So nothing is present before 0. And, everything, whatever it is, everything starts at time 0. So I could just integrate from 0 because there is nothing to integrate before time 0. So I can just take it from 0. Okay. All right. So we've basically come full circle. So we've got the two responses, the 0 input and the 0 state. We see the 0 input both in the time domain and the Laplace domain. In the time domain, it's EH to the T. In the Laplace domain, it's the resolvent, okay, times x of t. And then we see that the 0 state component is actually the convolution in the time domain. And in the Laplace domain, it's the product of two transforms, okay? And I'll just reiterate that the product of the two transforms are actually that, okay? Where h of s is the transfer function. All right. So let's get back to the 0 state response. Now that was the full response. Let's get back to the 0 state response when the x of t is 0. So I'm just left with this. So that's the time response if I were to change the input without changing the state variables. If q of t is an impulse, all right, it turns out it's quite straightforward to reduce this actually. First thing to note is there's a shifting property which I briefly mentioned in the signals chapter, which talks about the impulse and how we can basically pluck out a value for a function. So if you have a function f of t and you apply an impulse at say a, it'll effectively pluck out the value of f of t and give you f of a. Okay, so it's called the shifting property, and we can basically use that in this case. So f of t is equivalent to EAB. So that's the f of t. And then this is the impulse. And I'm applying an impulse. If I apply the impulse at A, I effectively get this, right? So if I apply a unit impulse to the system at time 0, I basically get this, right? So that's the time domain solution for an impulse. So right, so for a unit impulse. Okay, for a unit impulse. All right. So it's easier to see this result though in the Laplace domain rather than going through all this shifting property stuff. So if I take the Laplace domain for a zero state, all right. So there's the resolvent, all right. Then there's B and there's Q of S. This whole piece here is the transfer function, okay, all right, indicated by H of S. So effectively, X of S is then H of S times Q of S, where H of S is this. And if I take the inverse, if Q of S is a unit impulse, right, that means it's 1 for unit impulse, right? And then the impulse, then the inverse of this then just drops back to that, because I know the resolvent is e to the at. We've seen that before, right? And that's effectively the same as this, okay? So it's easier to get this from the Laplace transfer domain than to go through the shifting property. But this piece here is a key equation, not the Laplace domain response is the transfer function times the input transfer function. Okay, and this is why I put, up here, I put this thing here, right? Except it should be the other way around. This is the scalar form, but when you do the matrix form, the Q is actually on this side, right? Which is what I got here. Okay, all right. Okay, let's look at this example again. We saw this before at the beginning. This was this simple system. It was X, that was K. I have K2X here instead of just K. And then this was the input, which I hadn't specified. All right. So I can get X quite easily, get H of X quite easily. I set the initial conditions to 0. So I'm going to compute the zero state response. Okay. So I take the Laplace transform on both sides. Q of T turns into Q of S. So I'm not interested in any specific signals, so I'll just call it, oops, sorry. So I'll just call it Q of X, right? So if I solve for X of S, I get this here, right? And you can see that this is of the form X of S equals Q of X times something. Of course, that something has to be the transfer function. Okay, so the transfer function is 1 over S plus K2. All right. I can take this, I can specify an actual input. So let's say it's K x0 times K1, and we'll make it a step input signal of strength size x0. I can do exactly the same thing. I can transform both sides. I can rearrange to solve for X of S, and I get this. This piece. So this piece is the Q of S. This is an important point, right? Here, because the actual transfer function is this. So it's that bit, all right? So the K1 is part of the transfer function. The X of S is actually the Q of S. And if you're a bit confused by that, there's a better way easier way to think about this in terms of the LTI. Remember the LTI matrix, we had dx dt equals ax plus bq. Okay, I'll call it q, not u. Remember how do we compute these? This was dx by dt by dx, right? And the b was dx by dt dq, right? So if I want to get a, right, if I want to get a, I have to differentiate this with respect to x. So that basically leaves me with just minus k, k2, right? That's right. That's easy enough. If I want b though, so I have to differentiate this now with respect to q, and q, as I said, the input was x0. So if I differentiate that with respect to x0, I get k1, right? And that's why the k1 appears here, okay? So the b includes the k1. And if you think about it, remember that the transform of this system was the resolvent times b, and I know b is k1. So b is k1, that's the k1 there, and the resolvent is just 1 over s plus k2. Okay. Maybe I should show you that where that is in fact the case. So if I want to evaluate this, right, it's s times I. Now there's only one state variable, so I is 1, right? Minus a is minus k2, so it's basically plus k2 to the inverse. Okay, and that's what I get there. Okay, so that's where that came from. All right. So now that we've talked a little bit about this transfer function, let's delve a little bit more deeper into the transfer function because it turns out to be a really fundamental entity in control theory. So let's just have a reminder. If I have this general system here, okay, take the transforms on both sides and then solve for x of s, I get this. This piece here is the transfer function. Okay, includes b. Okay, includes b. So here we go. Yeah, SV is called the transfer function. It's also called the transfer function matrix, or more simply, the transfer function. So this is actually we've seen this a couple of times now. The transform of the state variables is the transfer function times the transform of the input. This thing you should burn into brain. Okay. All right. Now, if it's now these are matrices, okay? So you can imagine then there must be, this H matrix has a whole bunch of individual transfer functions inside it, and that is indeed the case. In fact, if there are n state variables and p inputs, the size of the transfer matrix is an n pi b matrix, right? So if I have 4 state variables, and 2 inputs, the number of individual transfer functions in H will be 6. Okay. If I were to pick out any one of those 6, now these are now scalar equations now. If I were to pick out any one of those 6, I can define that individual one, see H of S, is the individual X of S that corresponds to that entry divided by the transform for the input that's applied to that entry. Okay, and this is a common way of looking at it in the scalar form, and in that form you can see that the transfer function for a given state variable and a given input, actually that should be input is defined as the ratio of the, oh, hold on, no, that's true, that's right, hold on, that was my mistake here. Yeah, so the transfer function for a given state variable is given by, that should be a by, given by the is given by the is given. No, that's terrible. Let me see. Transfer function for a given state variable is defined. Yeah, is defined. There we go. Is defined as the ratio of the output x of s to the input Q of S in the Laplace domain. All initial conditions are assumed to be zero, of course. This is the zero state response. So this is why people often talk about the transfer function as, you know, it's the relationship between the output and the input, right? So this is the output and this is the input, right? So the transfer function is the relationship between the output and the input, okay? So it's tied between a specific output and an input. Okay. A little bit of terminology. It's not important terminology, but you'll see it in the textbooks. If a system has a single state variable and a single input, then it's called a single input, single output system, or SISO. If a system has multiple state variables and multiple inputs, it's called a multiple input output system, or MIMO. Okay, that's just a notation. You'll see that in some textbooks. SISO and MIMO. So, for example, a SISO system is this. Oops. A SISO system is this. If I have x0, I have a single input, let's say, and I have a single, you know, state variable. That's a SISO. Okay. If, on the other hand, let's say I had two variables, right? Could be two capacitors or two species in the pathway, and I've got three enzymes. All right. And my enzymes are my inputs, and my two x's are my outputs, then I'll have a MIMO system. Okay. All right. Okay. Let's look at transfer functions again, more detail. Remember I said, now we've agreed that this is in the scalar world. If you pull out any one of those entries from the H matrix, right, where we had a bold H, pick out any one of those. It turns out that, I'm not going to give you the proof, but the proof is in the textbook. It's actually a ratio of polynomials. All right. So the transfer function is a ratio of polynomials. All right. And so these are the ratio of polynomials here. Okay. I can write it out in a more sort of generalized form where I've sort of factored out all the terms in the polynomials, right? When you do that, you end up with a factor at the beginning, which is called the gain. Right? It's the gain factor. And you get, you know, this ratio of factored polynomials. I'm going to give them the symbols B of S and A of S, right? Because, now here it is again, because the denominator A of S, this piece here, turns out to be really, really important. If I take this out and set it to 0, it is called the characteristic equation. The characteristic equation you'll come across all over the place in engineering. And it's basically the polynomial in the denominator. Those of you who might remember, we were computing things like, you know, when we were computing the solutions to the homogeneous equations, we were having to take the inverse for the matrix, and one of those, and we had to find the determinant. All right, that's basically this. That's basically the determinant of those matrices we're looking at. And in engineering, at least, the roots for the characteristic equation are called the poles. Right, that notation pops up all over the place. Right, so the roots of the characteristic equation are called the poles. And likewise, we also have a polynomial in the numerator, and the roots of the numerator are called the zeros. Okay, so poles and zeros. All right. The other thing, a bit of notation, is the order. So the order of a transfer function is the order of the characteristic polynomial. That's the highest power of S in the denominator. So, for example, here's a transfer function. This S plus K2 is the characteristic equation. What's the order of that? Well, the highest order here is S to the power of 1. Therefore, this is a first order system, right? So this is a first order system. That's why I've been calling this a first order system all along, because the highest power of S is 1, hence is a first order system. Here are some examples of other transfer functions. We can figure out what the orders are for these. So although you've got s to the power of 1 and s to the power of 1 here, actually when you multiply it out, you get s squared plus s2. So this is a second order system. Right? Second, well, let me do that properly. Second order, okay? Because of the highest order is 2. This one, if I multiply all the s's out, the highest one I get is s cubed. So this is a third order system. Okay. This one also is a third order system. And this one, finally, this one, the highest order is s to the 4. So this is a fourth order system. Okay. So in order to decide the order of the system, you just look for the highest power in s in the denominator. All right. So you can see these are all polynomials. Okay. Okay, and if you look to this one here, right, you can tell immediately what the poles are. The poles are, there's 3 poles, and they're -1, -2, -3. Okay. All right. Let's look at the denominator even further. So let me write down the transfer function in this form. I don't care about n, the numerator, but I've factored out the denominator polynomial. These are in the individual poles. Okay. All right. I can do a partial fraction expansion on this. It's a simple product of terms. So the partial fraction will look like this. It's just a sum of things. As I said, I don't care about the numerator, but the denominators are all split up like this, taken from each factor in the denominator. If I take the inverse transform of this, I get this. Okay. So I'm taking the inverse transform of the transfer function. You see that the p's, the poles, all end up in the exponents. And of course, we know what those exponents were in the time domain solution. They were the eigenvalues. Therefore, the poles are the eigenvalues. Okay. So engineers like to call them poles. Mathematicians like to call them eigenvalues. I'm sure there are other people that call them different things as well, but the poles and the eigenvalues are the same thing. Okay. Yeah. So the poles are the eigenvalues of the A matrix. Okay. Why am I talking about poles and stuff? Well, historically, control theory has spent a lot of time investigating the poles of the characteristic equation, how they behave, and we'll be looking at that in detail next week when we come to look at stability in particular. Okay. So just an example, here's my transfer function. It's a first order system, as you can tell, because the highest power is 1. Let's assume b is positive, okay? Then the pole is minus b. And if I were to take the solution of this, I would find it's just that, okay? Because that was the eigenvalue. The eigenvalue was minus b, all right? So the poles are the same as the eigenvalues. The other thing that engineers like to do a lot is they like to plot the poles and the zeros. In the poles zeros plot. Okay, it's common. It's very common to see the poles and zeros plotted in something called the pole zero plot. Now, what do I mean by that? Now the poles, you have to remember the roots here. I mean, the roots of a polynomial can be real or complex. Okay, so when we talk about plotting the poles and zeros, basically you're plotting it on an Argon diagram where I have the imaginary part on the y-axis and the real part on the x-axis. Okay, so the roots of a polynomial can in general be complex. If they're complex, they'll have an imaginary part and a real part. I can separate those out and then I can plot a point, right? So that means that this particular root had an imaginary part of this value here and had a real part of this value, okay? Now, if your root only has a real part, then it'll be on the line, the real line. If your root has only an imaginary part, then it'll just be on the imaginary line, okay? So it's a two-dimensional plot, right? Also, by convention, the poles are often indicated using crosses and the zeros are often indicated using circles. All right. So you might see something like this. Okay. So here's the imaginary part and then here's the real part. So here are two poles, and there's 1 0 down there. All right. So the two poles are on the 0 line itself. They have two imaginary components, but no real component. The 0, which is the root of the numerator, has a real part only, and it's sitting on the real axis. Okay. I came across some software that you can use in Python to compute this, and I will demo this on Tuesday. That you can use to plot. It's pretty simple. There's actually there's a SciPy signals package that has this function called TF2ZPK, oddly named thing, but it stands for transfer function to zeros and poles. There you go, right? Transfer function to zeros and poles. What you have to do is you have to give it the coefficients of the terms in the polynomials in the numerator and the denominator. I just did here one, just for a demonstration, 1, 2, 3, 1, 2, 3, 4, 5. But for a first order system, right, you might have something like 1, and then you might have something like 1, 5, right? That would be a first order system, right? So this piece, that function call here does that, right? It's expecting the numerator followed by the denominator, and returns the zeros and poles and the gain. Okay, and then this just plots it. This just plots it. And then here I just return the zeros, poles, and gain. So if I do that on this example here, I get this plot. Okay, so this is the imaginary axis, real axis. Here are the two zeros, and then there's 4 poles. Okay, 4 poles. All right. All right. The other thing is you'll see transfer function also written what's called a standard form. This is done for 2 reasons. One, it's easier to read off these zeros and poles because you don't have to do a mental sign change. That's not really that important. But the real reason why people used to do this was because for constructing Bode plots, and I know you're aware of Bode plots, but the manual construction of a Bode plot, which is a frequency response plot, was much easier if you expressed your transfer function in this form. Not so important today, I guess, although a lot of people swear you should be doing this manually anyway, just to get a hand, get an idea of how Bode plots look like depending on the transfer function. These days, of course, you can do it by computer, so maybe it's not so important. But anyway, that's just that you're aware of it, that there's a standard form. Okay, so that's as far as I'm going to go with transfer functions today. We will look at them a lot more later on, especially when we come to do the frequency response and stability. The last thing I want to finish off with for transfer functions is this thing called the final value theorem. Okay, we didn't manage to finish this off last week, so this is an opportunity for me to talk about it. The final value theorem, this is it. Right, it looks a bit weird when you first see it, but it lets you compute the steady state of the system given the transform given x of s. Okay, all right. I think I got that right. X of s. Yeah. So given x of s, what can I say about the steady state of x for the system? And what's amazing about this final value theorem, it'll take the transform, right, x of s, and give you immediately the actual steady state value. You don't have to do the inverse transform or anything. If you do this, it gives you the value f of t at infinite t. Okay, all right. So let's see this in operation. So here's my model. All right, this is the input. In this case, the input is just going to be a step input, right? So I'm going to take what's going to look like is this. That's time. So basically, x is going to start here, right? So that's x of 0, right? It's going to start there. And I want to know what is the steady state for this system when x of 0 is like this, right? So it's not changing in time. It's a step input. Okay, so we have 2 state variables, x of 1, x of 2. These are the differential equations. Here's the input. Okay, I can take this. I need to compute the 2 transforms for this, not the transfer function, but the two transforms. We need to basically compute that, okay? Okay, that's what I'm basically computing. For the first one is this. There's the Q of S, and there that is actually the transfer function. And this piece here, this piece here is Q of S. Then this chunk here is the transfer function. Okay, but I need the full transform, right? So what I need to do, I need to plug these into basically here. And so what it does is, I've written it down here again. So what you do, you have to plug X of S into here, multiplied by S, and then take S to 0, right? That's what you have to do. Now, there's one caveat. This only works if the system is stable. You cannot do this, cannot use the final value theorem if it's unstable, all right? You get weird results if you do it when it's unstable. If it's stable, though, in other words, remember what we said about stability? Stability you get when the eigenvalues are negative, right? So if the eigenvalues are negative, it's stable. Now that we know that engineers like to talk about poles, it also means that if all the poles are negative, the system is stable. And we'll come back to this again, actually, but it means also that if all the poles are in the negative quadrant, or the left quadrant, the system is stable. If you have any, if you have any X in the positive quadrant, you know the system is unstable, all right? We'll come back to that again another time, but just want to mention that. Okay, so so this system is stable. Actually, I know that because all the roots are negative. Okay, all the poles are negative. Here as well, negative. So what I need to do is then I need to take the x1 multiplied by s. Notice the s's cancel, right? That's nice. And then I have to take s to 0. So s goes to 0, and I'm basically left with this. That is the steady state level of x1 as t goes to infinity. To do x2, I insert it here. So this is x2. I multiply by s, cancel, and I'm left with this. I take s to 0, so basically these disappear, and I'm left with this piece. Notice the k1s cancel, and I end up with that. And that is actually the steady state level for x2 as time goes to infinity. Okay, I think that's it. We've come to the end, okay? All right, so that's chapter 12. This will be uploaded to YouTube very soon. So I think we're done, and I'll shut down the recording.